Hello and welcome to Earthquake Tip number 6. My name is Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these steps, our aim is to spread right technical information in simple to understand language to our professionals who are in the field, designing and constructing structures, especially architects and engineers. Before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip number 6 is about how architectural features affect buildings during earthquakes. It's important to note here that architectural features such as overall shape, size, and geometry plays a critical role on behavior of buildings during earthquakes. Hence, at planning stage itself, architects must ensure that unfavorable features are avoided and a good building configuration is chosen for better seismic performance. The famous earthquake engineer of USA, late Henry Deng Cobb, summarized the importance of configuration of building as, I quote, if we have a poor configuration to start with, all the engineer can do is to provide a band-aid, improve a basically poor solution as best as he can. Conversely, if we start off with a good configuration and reasonable framing system, even a poor engineer cannot harm its ultimate performance too much. I unquote. Now let's look at the architectural features. Let's first begin with size of building. As shown in figure 1A, the tall building with large height to base ratio, the horizontal movement of forces during ground shaking is large. Whereas in a short but very long building, as shown here in figure 1B, the damaging effects during earthquakes shaking are many. As shown in figure C, buildings with large plan area, the horizontal seismic force can be excessive to be carried out by columns and walls. Now let's look at the horizontal layout or plan of the building. In general, simple geometry in plan as shown in this figure 2A have performed better during strong earthquakes. Buildings with reentrant corners such as U, V, H and plus shaped as shown in this figure 2B have sustained significant damage during earthquakes. The common solution is to make buildings in two parts as shown in this figure to see this L-shaped building can be broken into two rectangular plans using a separation joint at the junction. Now let's go to the vertical layout or elevation of the building. The basic philosophy of earthquake engineering is to bring down the earthquake forces developed at different floor levels in a building to the ground along the height by the shortest path. Any deviation or discontinuity in this load transfer path results in poor seismic performance. For example, building with vertical setback as shown in this figure 3A, like the hotel buildings with few stories wider than the rest, cause a sudden jump in earthquake forces at the level of discontinuity. Similarly, buildings with fewer columns and walls in a particular story or with unusually tall story as shown in this figure 3B tend to damage or collapse during earthquakes. During 2001 Bhuj earthquake, many buildings with open ground story intended for parking collapsed or severely damaged. Figure 3C, as you see, is a building on slopy ground having unequal height of columns along the slope. This also causes ill effects like twisting and damage in shorter columns. Building with columns that hang or float on beams at intermediate story and do not go all the way to the foundation, also known as floating or hanging columns, have discontinuity in the uh, load path as shown in this figure 3D. Sometimes buildings have reinforced concrete walls to carry the earthquake loads to the foundation. Buildings in which these walls do not go all the way to the ground but stop at the upper level, as shown in this figure 3E, are liable to get severely damaged during earthquakes. This figure 4 talks about adjacency or closeness of building. When two buildings are too close to each other, they may pound on each other during strong shaking with increase in building height. This collision can be of a great problem. This particular figure shows when building heights do not match, the roof of the shorter building may impact the mid-height of column of the taller building, which can be a dangerous preposition. At last, let me tell you that architectural features are normally introduced with a desire to create an aesthetic and functionally efficient structures. Sometimes the shape of the building catches the eye of the visitor, sometimes the structural system. In other occasions, both shape and structural system work together to make the structure a marvel structure. Nevertheless, each of these choices of shape and structure has significant bearing on the performance of building during a strong earthquake. The damages during past earthquakes across the world have been very educating in identifying the shape and structural configuration that are desirable versus those which must be avoided. We will continue to make buildings interesting rather than monotonous, but this need not to be done at the cost of poor behavior and earthquake safety of buildings. Architecture features that are detrimental to earthquake forces should be avoided. If not, they must be at least minimized. It is to be worth mentioning here that when irregular features are included in the building, a considerable high level of engineering effort is required in structural design, and yet the building may not be as good as one with simple architectural features. Although building design and codes are available, but architectural features made at the planning stage on building configuration are known to have made greater difference than accurate determination of code specified design forces and structural design. In summary, simple symmetrical structures in plan and elevation without any abrupt change in beam column configuration and continuity are key to good seismic performance of the building. With this, we come to the end of this earthquake tip. You can download earthquake tip from www.bmtpc.org. Next earthquake tip, that is tip number 7, will be on how buildings twist during earthquakes. Thank you very much.